Okay, Chem 212 students, welcome to our Week 7 first lecture. This week we're covering Chapter 6, so it's all about chemical reactivities and the way to draw arrows to show mechanisms. So we've seen one type of this in the past with acid-base, the proton transfer part of a chemical reaction mechanism. We're going to go into more other different types of steps and demonstrate how to draw the double-headed arrows for those steps. Okay, let's get going. First of all, if we want to talk about chemical reactivity and whether a reaction will happen or not, we need to think about the energies of the reaction and the entropy. So in terms of energy, we're looking at specifically here the heat energy, also called the enthalpy, or delta H or Q, the heat energy exchange between the reaction and its surroundings. So breaking a bond requires energy. You have to pull those atoms apart. And in that energy required from a molecular orbital perspective is required because the electrons in the bonding molecular orbital are lower in energy than each of the individual atomic orbitals. And so energy must be put in to split those atoms apart and then make separate atomic orbitals. So bonds can break in two different ways. They can break either homolytically, meaning that when the bond breaks, each of the atoms gets one electron, or they can break heterolytically, which is going to be most of the situations we're talking about. This is where both of the electrons in a bond go to one of the atoms, leaving one atom with one fewer electrons, thus having a positive charge, and leaving the other atom with an extra electron, thus having a negative charge. And so when we're going to look at a few examples of bond dissociation energies, these generally are corresponding to homolytic bond cleavage. They are also useful in heterolytic and in looking at reactions that undergo heterolytic bond cleavages. They'll give you a relative idea of how much energy you would have to put in to break a bond. Okay. So here are some examples of bond dissociation energies in kilojoules per mole and also kilocalories per mole, which is still fairly common to use, although kilojoules is the SI, the approved SI unit that we should all be using, but calories are still in common usage. And you'll see a few patterns. First of all, hydrogen-hydrogen bond, for example, is very short because the atoms are so small. And so the bond energy is quite high. It's high for a CH bond or HH bond, about the same energy. You have a CH bond in a larger molecule. Here you see it's a little bit smaller. And then for the bonds between hydrogen and halogens, you can see that it's the largest for HF. Again, shorter bonds here are stronger, and H and F are both very small. This makes for a very short, strong bond. You can see these get weaker as the atom gets larger. In water, the bond between hydrogen and oxygen is fairly close to that as for HF, right? So 498 kilojoules. Also another short, quite strong bond. And then we have here various bond energies for carbon-carbon bonds, and we can see that the energy here in ethane is a little bit higher than it is in propane, and so forth. But they're all around 360-ish kilojoules per mole. And then you can see again here, bond between carbon, bromine, carbon, iodine. The bond is weaker for the bond between carbon and iodine because it's longer. And so you can get a really good idea of bond energies based on these types of comparison or common bond energies, which can influence the way you think about the way a reaction will happen. It's harder to break stronger bonds. It's easier to break weaker bonds. When it comes to halogen-halogen bonds, we can see that although this bond is very, very short between fluorine and fluorine, it's very weak as well. And this has to do with the fact that both fluorine atoms are very electronegative. And so they kind of both want to pull on the electrons in the bond, and that kind of pulls the bond apart. And so that's the other factor when it comes to bond energy, is if one atom is electronegative and the other is not, a short bond can still be quite strong, as you can see here. when you have two electronegative atoms pulling on the electrons in the bond, that can weaken the bond, and that's the case here. So this is some just general trends in bond dissociation. And so here we have a list of a few bond dissociation energies, and the question says, use bond determination energies to determine if the following reaction is exothermic or endothermic. And so here we have a reaction, and in order to figure this out, we have to figure out which bonds are broken. Those are going to be endothermic. You're going to have to, whoops, and sorry, these words are backwards here. Endo, exo. Sorry about that. Endo. And so we want to determine if the reaction is endothermic, in which it's absorbing energy, which is a positive delta H, or exothermic, which means energy is leaving the reaction. That is indicated by a negative delta H. And so to figure that out, what we'd have to do is figure out which bonds are being broken. So bonds broken. And we want to figure out the bonds formed. And so these are going to be positive in energy. Bonds formed. And when the bonds form, they're going to release energy. So that's going to be negative. And so it's going to be bond broken minus bonds formed. And so in our bonds broken here, we're going to have to break a carbon-hydrogen bond. And we're also going to have to break a bromine-bromine bond. And so we see that a carbon-hydrogen bond, we're going to have to break one of those. It's going to be 397 kilojoules per mole. For that, we have to do one of those. And we also have to break a bromine-bromine bond. And so it's going to be plus 1 times positive 193 kilojoules per mole. Okay. And now we're going to have to subtract the bonds created. And so we're going to create here a bond between carbon and hydrogen. And so this is going to be between carbon and bromine. So this is going to now be 285 kilojoules per mole. And this is going to be energy that's released. That's why we have a negative here. And then finally, we form a bond between hydrogen and bromine. That is going to 1 times 398 kilojoules. And I wrote the positive here just to emphasize. Here, we're going to have to put energy in to break it, and then we have a negative here, meaning energy is going to come out. And so when these bonds form, the energy is. So now we need to use a calculator. Oh no, I lost my writing. Okay, so let's get the calculator out. So just to repeat it here, so we're going to be putting in the bonds that we're breaking, which includes a carbon-hydrogen bond right here. And so it's going to be carbon-hydrogen 397. We're going to add to that the energy required to break the bromine-bromine bond, 193. And we're going to subtract the energy released when a carbon-bromine bond is, so minus 285. And we're going to also subtract the energy that's released when a hydrogen and bromine bond is 368. And so we get negative 63. And so the delta H here of this reaction, negative 60. And again, that was by adding the bond energy, bond dissociation energy for CH plus bond dissociation energy for bromine 2. That was 397 plus 3. And then we're going to subtract the energy released, carbon bromine 285 and we're all killing all. And then we're also subtracting out here the hydrogen bromine bond energy. Subtract both of them. 5 plus this is bond dissociation. Bond energy of carbon to bromine here. Bond dissociation energy of this one, hydrogen bromine. So bonds broken minus bonds formed. Positive here for bonds broken because we have to put energy in. Negatives for bonds formed because energy comes out. Energy bonds are formed. We got negative 63. Okay. So let's talk now. Usually we don't care about the numbers exactly, so we calculated exact numbers. But you notice that I was kind of describing to you how to kind of generally have an idea of how big the bond energy is. This is because usually we want to kind of be able to just kind of guesstimate a little bit. That's the easiest way because we really just want to know, is this reaction exothermic, meaning is it delta H negative, or is it endothermic, delta H positive? So generally, when bonds are formed, energy is released. When bonds are broken, just think about pulling apart the bond. It takes energy to pull apart, like pulling apart two magnets, right? And so if H and F, they're free radicals. Free radical means atoms with unpaired electrons. We'll talk about those later. You can see here a homolytic bond cleavage produces free radicals. We'll talk about those in chapter 11. But going the opposite way, and those atoms coming together, they will form a new lower energy molecular bonding molecular orbital. Thus, energy will be released. So this is going to be delta H is negative. Delta H negative. So negative is exothermic, release energy. Carbon-bromine bond is broken. That means we got to put in energy to pull it apart. So here the delta H positive. A strong bond is broken and a weak bond is formed. And so this means we're going to have a large positive component and a small negative component. We're going to have to put a lot of energy in to break the strong bond, but we're going to not get a lot of energy back when the weak bond is formed. So here delta H will be positive. This is exothermic, or endothermic rather. It's going to require energy. If we break a weak bond, that means we don't need to put that much energy in, so the positive part will be small and we'll add that to a very large negative part. When a strong bond is formed, that means a lot of energy. So here delta H negative. So in terms of energy diagrams, so we're going to be seeing a lot of energy diagrams in this chapter and as we move forward later on. And so you're going to want to be able to analyze these and show what they mean. So if we have some starting materials here, these starting materials start with a high energy, but in the end the products are at a lower potential energy. That means along the way energy was released. Now there's a little bump here. This, if you remember from Chem 151, represents the activation energy. That has to do with the kinetics or the speed of the reaction. We'll talk about that in a moment. But right now we're talking about the thermodynamics, and that's it. That has to do with the energies of the starting materials, the starting potential energies, and the energies of the products, so the ending potential energy. So since the products have less energy than the starting materials, energy was lost during the course of this reaction. Heat energy. And so this is an exothermic reaction with a negative delta H. When the starting materials start with less potential energy than the products, then energy must be put in to get to the products. And so energy being put in is positive. So I remember endothermic as N sounds like in. So energy is going in. We have to put energy in to get to the products. And I remember exothermic, like exit. The energy is leaving the reaction. So it's exothermic. The sign here is negative for exothermic, positive for endothermic. And what's important, an important thing about this is what happens to the surroundings. And this is going to become important when we talk about entropy. But when energy is released, that will generally cause the surrounding temperature to increase. So for an exothermic reaction, the temperature of the surroundings will increase. Whereas here, here in this case, so that this phrase here would be corresponding to this exothermic situation. Whereas here, this is an endothermic situation. So it's going to be pulling energy from its surroundings. And so the temperature of the surroundings will decrease. So most reactions are exothermic. And this is probably consistent with your everyday experience when you see something burning or something, energy is being released. But there are many endothermic reactions that occur. And this has to do with the fact that not only does the enthalpy change in the reaction matter, but also the change of a property called entropy. So enthalpy and entropy must both be considered. And entropy can be thought of as molecular disorder or randomness or freedom. When the atoms can move around more freely, that's greater entropy. And when they're more locked in place, that's lesser entropy. More accurately, from a statistical view, entropy can be viewed as the number of states that a molecule can occupy, and this is a great number of states. It can include the position of a molecule, its orientation, and all other things that describe its movement, its speed, and so forth. So this includes like also vibrational states, rotational states. So we've talked about cyclohexanes and sigma bonds that rotate and spin, and the cyclohexane goes between does chair flips and so forth. So that's a kind of freedom as well, freedom for bonds to rotate, and so the greater rotational freedom as well. So here, which molecule would have greater entropy? So molecule will have greater entropy if it's got more atoms. Therefore, there would be more ways for it to orient itself. These both contain approximately the same number of atoms: 1, 2, 3, 4, 5, 6. 6 carbons. This one has a couple more hydrogens than this one, but that doesn't make much of a difference. What really makes a difference is that in the cyclohexane, the carbons are locked into a ring formation, so the bonds cannot freely rotate around and around and around. However, here, if we're looking at this bond or this one, these bonds can all rotate and wiggle around, and there's lots of freedom of rotation. So this molecule is going to have more entropy, and this molecule will have less entropy. Because of the fact that, again, it's locked into place rotationally. It can rotate a little, it can do a chair flip, but not as freely as this. What about for this? So remember that the entropy has to do with the number of possible states and orientations that these molecules can occupy. And so it is an example of how kind of an example that you can understand or that's normal to everyday life that explains what entropy is. So let's say you have all these air molecules trapped in your tire, and then this is the outside. So when you open the valve, the air molecules rush outside of your tire really quickly, and they go to fill up the space outside, right? In this case, it's another glass bulb, but in your real life, it might be your tire. The air never goes back into the tire on its own, right? It always comes out. And so that's an example of a process. This is just a physical process, the movement of molecules, that's driven by entropy, because there's more possible states for the air molecules when they leave your little tire here and have more space to move around than if they were stuck in the tire. So that's the driving force behind why the air comes out of your tire but doesn't automatically go into your tire. greater entropy when the air molecules can go anywhere they want. Now, when it comes to entropy, it's not just the entropy of the system that we're thinking about. So, for example, the system, let's say, being your tire. Now, we're also interested in the surroundings, right? And so that's something we have to think about, especially if we have a reaction that's releasing a lot of heat energy or absorbing a lot of heat energy. Because if a reaction is releasing a lot of heat energy, then the surroundings are going to get hotter, and the molecules will move around more, and that will be more entropy. And so we have to think about both the system and the surroundings when we think about the entropy. You can think about the entropy of everything. And this, if the total entropy for the system and the surroundings is positive, then the process will be spontaneous. It will go on its own. If delta S is negative, the process will not be spontaneous, and you'll have to put a lot of energy in to make it go. For example, if we're going back to the tire, you have to put a lot of energy from a pump in to push more air molecules into the tire, and then you can overcome the entropy. But it takes energy. So when a volume of gas expands to fill in a container, what should be the delta S of the surroundings? It's a good question, right? And it depends on what's happening to the surroundings. For chemical reactions, we have to consider the change for both the system and the surroundings. The surroundings is usually a solvent, although it could be air, surrounding air, and so forth. So here, if we look at this, for this reaction, we have a molecule composed of two atoms, and then those atoms break apart. When we have one molecule break apart into two pieces, this is an increase in. So this is delta S here, positive for this reaction. So delta S positive, it's an increase in entropy, because these atoms have more freedom of motion. They can move around wherever they want, whereas here they were stuck together. They didn't have as much freedom to move around. Or here, if we have a cyclic compound, it breaks into an acyclic compound. This is also delta S is increasing. So we have a increasing entropy, because now as a straight chain, all these bonds can rotate and they can wiggle around in any way they want, whereas when they were in a cyclic arrangement, they didn't have as much freedom to so when a molecule structure, when we have these kinds of changes over the course of a chemical reaction, this will be an increase in it. Now, this is all talking about the system, the reaction itself. What about the surroundings? Well, the delta S of the surrounding is going to mainly depend on the delta H of the system. Again, if it's releasing energy, that's going to increase the temperature of surrounding molecules, which will increase their movement and thus increase their entropy. So the entropy of the system can easily be measured, but the entropy of the surroundings depends on the system. The exact relationship is the delta H of the system divided by T, which is basically saying that the more that the temperature changes, because of delta H, that's going to increase the delta S surrounding. Now, notice the temperature here is on the bottom. The reason why is because if the temperature is already low, even a small delta H can change the temperature significantly. Imagine that you have a surroundings, the temperature is 1 Kelvin, and then after the reaction, it goes up to 2 Kelvin. In that case, because your temperature was so low, this small change in energy was a great change in temperature. But if you're doing the same thing, but going from like 300 Kelvin to 301 Kelvin, well, relatively speaking, that's a small change, but it would take the same amount of energy to achieve the same change in temperature, 1 degree Kelvin. And so, this delta S surroundings is not directly proportional to the delta H of the system. It depends on what temperature it started at. But also it's negative, meaning that if the reaction is exothermic and releasing energy, then that means that, so we have some reaction, it's exothermic, so let's say it's going in here, it's releasing energy, then the temperature of the surroundings will increase. And so a negative delta H indicates an increase in entropy of the surroundings, because when the energy is released out to the environment, the temperature of the surroundings increases. Molecules can move around faster and more freely, thus you have a greater delta S of surroundings. So if we take this part and we plug it in, take this part and we plug it in right here, then we have this delta S system plus this delta S surroundings, which we've replaced with negative delta H system over temperature. That is the delta S total. And again, that's what we want to know, really. The delta S total will tell us if a reaction is spontaneous or not. It all depends on the delta S total, or what's also called the delta S of the universe. Now, the problem is that measuring the delta H of the system is relatively easy. Measuring the delta S of the surroundings was difficult. So that's why now we've got the delta S total written in with respect to all the system. And the system is a lot easier to measure than what's outside of the system, because the system's what we're focusing on. And so what we can do here is we can use this as a means of deciding if the reaction is spontaneous or not. Again, the reaction will be spontaneous if the delta S total is positive. This is going to mean a spontaneous reaction. And if it is negative, this is going to mean a not spontaneous reaction. It will not go on its own. And so what we want to know is we want to know this delta S total. However, this equation is a little bit cumbersome, so we can simplify it by multiplying each side by negative t. So if we multiply each side by negative t, then this negative t will cancel here. This will be negative t, so we have here negative t times delta S system. That's taking it right here. And then when we multiply it right here by this term, the negative and the t cancel. Just end up with just delta H of. On this side, we have negative t times delta S total. And this is going to be a quantity that's defined as delta G, or the change in the Gibbs free energy. Gibbs free energy, delta G. And this is going to be delta H of the system minus T delta S of the system. Again, notice that this is all defined relative to the system. So at this point, we drop off the system and we just assume all of this is now talking about the system or the reaction that we're interested in. So how will the sign positive or negative for delta G affect spontaneity? Well, we said that a reaction will be spontaneous if the delta S is positive, delta S total. So the delta S, if the delta S total is positive, that means that the delta G will be negative. So if its delta G is negative, we say that's a spontaneous reaction. And if delta G is positive, we say not spontaneous. And so now, from now on, instead of talking about delta S total, it's much easier to simply talk about the system. And so now this is defined as the delta G of the system. So everything now is with respect to the system, which makes things just easier to analyze. So let's think about this example here. Remember, we did do a calculation of delta H. We haven't done any calculations for delta S, and we don't really need them. All we really need to know is the sign of the delta H and delta S. So here we can see that in this reaction, it was required for us to to create bonds here. In this reaction, bonds were created. And so since bonds were created and not any except for this pi bond here, which is kind of a weak bond, were created, we're going to have here a negative delta H reaction. So this delta H here is negative. We're going to have these strong sigma carbon-carbon bonds being formed right here. We're going to break some pi bonds, but that's not going to really require much energy. We're also going to add additional bonds between carbon and hydrogen. So we're going to have a lot of bonds being created here. And so that's going to mean a lot of release in it here. So delta H is negative. However, when it comes to the entropy, we can see that we're going from two separate compounds to one. So delta S here is going to be positive. Now, when it comes to the spontaneity, we can analyze the reaction delta G equals delta H minus T delta S. We can analyze it in this way. We can think about if delta H here, if this is negative and the delta S here is positive, that means this whole term here will be negative if delta S is positive, because we have a negative of a positive. And so if delta H is negative and delta S is positive, delta G will be negative. Now likewise, if delta H is positive, but delta S is negative, that causes this whole second term here to be positive. Therefore, delta G will have to be positive. If delta H is negative, and whoops, I'm dead here about that. If delta H is negative, but delta S is negative, which causes this whole part to be positive, then positive here. If delta S is negative and delta H is positive, well, then it depends on how big these terms are, and that's going to depend on the temperature. So this is going to be when the temperature is large, this negative term is going to be large. So this will be so if this term is negative, so this will be negative at high temperatures, but it will be positive at low temperatures because it, say that right, this whole, whoops, no, I got that wrong. I got that opposite. Let's fix that. Sorry about that. Let's analyze this again. So the second term here is positive. So this term will get larger when the temperature gets larger. The positive term will be largest when the temperature is high. That will make this whole positive term higher. This will be positive at high temperature, and it will be negative at low temperature. And then finally, if it's positive here, and then delta S, if delta H is positive, delta S is also positive. That's behind my head there. This area here will be negative. So what will be the delta G here? I should have had that a little bit higher. I stuck under, but that will be negative at high temperature. So this will be negative. This term will be large at high temperature, and positive at low temperature. And again, negative delta G is spontaneous, positive is non-spontaneous. So here we have a negative delta H in our example and a positive delta S. And so we're in, we have a negative delta S. We have a negative delta S. Let's explain that again. We have a negative delta S because we have two pieces coming into one. And so we have lesser freedom of motion for these atoms because they were two pieces that could move around freely, but now they're one. So we are, in our analysis here, we are in this situation right here. We are negative delta H, so that favors spontaneity because that will make delta G more negative. However, we have a negative delta S as well. And so this is going to be spontaneous at high temperatures, but non-spontaneous at low temperatures. And that's really what we want to know. We want to know I wonder what conditions will this reaction be spontaneous, I wonder what conditions will not. So you can analyze approximate delta H's and S's. Notice I did not have to do a calculation. I knew delta H was negative because we're making lots of bonds and we're not breaking any except for pi bonds. Sigma bonds are much stronger than pi bonds. Then we knew that delta S was negative because we're having reduced entropy as two pieces. And then we can analyze if delta H is negative but delta S is positive, you will have a negative delta G spontaneous reaction. If delta H is positive but delta S is negative, you'll have a positive delta G reaction will always be non-spontaneous. But if you have negative delta H, negative delta S, the reaction will be spontaneous at high temperature, non-spontaneous at low temperature. You have positive delta H, positive delta S. It will be the reaction will be negative delta G at high temperature, so spontaneous at high temperature. Positive delta G at low temperature. That's right there. So that's the way that you analyze these reactions to see if they're spontaneous or not. Notice I did not have to do any calculation, right? I did not have to do any calculation per se. I just had to understand what causes delta H to be negative or positive and what causes delta. If a process has a negative delta G, that means it's spontaneous, and we say that the process is exergonic. So now we're focusing here on delta G, free energy, on the vertical axis. So that tells us whether the reaction is spontaneous or not. Again, if delta G is negative, that means it's a spontaneous reaction. If delta G is positive, that means a non-spontaneous. If a process has a positive delta G, that means the reactants here have lower Gibbs free energy products. Then the reaction is non-spontaneous. The reaction will favor the reactants at equilibrium. And what does it mean to favor the reactants? It means when you get to equilibrium, there will be more reactants for our products for a non-spontaneous. Going back for a spontaneous reaction, at equilibrium, there will be more products than there are reactants. A good question here. What does this tell us about the rate of the reaction? This doesn't tell us anything about the rate of the reaction. We want to know about the rate of the reaction. We want to look right here at what's called the activation. That's going to be the next topic up after equilibria. So if we have an exergonic process with a negative delta G, we say it's spontaneous. What that means is that if we have reactants A plus B and products C plus D, this means that if the delta G is negative here, this is telling us that this reaction is spontaneous. And so that means we're going to have more of the products at equilibrium than we have of the reactants. And the more negative the delta G is, the more products we will have. So in reactions, what causes the reaction? It's when molecules collide. Old bonds are broken, new bonds are formed, or sometimes in a single molecule, bonds will break often by colliding with another of the same. As we have less and less of the reactants, we have decreased collisions between reactants. So the forward reaction will occur less often. As the products increase, we have more collision between products molecules, and so that means the reverse reaction will begin to happen. C and D will collide with one another and go backwards and make A and B. At a certain point, the rate of the forward reaction will be equal to the rate of the reverse reaction, and that's called equilibrium. And equilibrium is considered dynamic, meaning that although it looks like once we get to equilibrium, no products are being formed, what's really happened is that products are being consumed at the same rate they're being formed, so their concentration is changing. But it looks like nothing. So here's a diagram of free energy on the vertical axis and concentrations of reactants and products. So on the left is all reactants, no products. On the right is all products and no reactants. And so we know that a spontaneous reaction occurs because it has a negative delta G, right? Spontaneous. Again, going back, this is a delta G is negative, or that's the same thing as saying minus T delta S here, that the delta S part is positive. Delta S of the universe, or delta S total. Say this is positive. That means delta G there is negative. So we can see that delta G is negative along the whole course of the reaction as long as we have a certain amount of A and B. But as the reaction proceeds, we're getting less and less of reactants A and B and more products C and D. And there's a certain point where if you're making more C and D, this reaction is no longer increasing in delta or decreasing in delta G. It begins to require delta G. So to get more and more products, that would be non-spontaneous. It's a certain point where we have a certain mixture of reactants and products, and we cannot get any more by a spontaneous reaction. That is the minimum value of the G, and that is called equilibrium. This is the largest possible total entropy as well, right? Related to negative delta G, positive delta S. So there's an intimate relationship here between equilibrium and the delta G. The equation you might have learned in Chem 151 is delta G equals minus RT ln K. And so here we can see that when delta G, so if we analyze this equation, we see when delta G is negative, that means that the K here is greater than 1, right? Let's imagine a few situations. If delta G is 0, okay, that means that the equilibrium constant is 1 because the natural log of 1 is 0. And so that would give you a delta G 0. If the delta G is negative, let's say, delta G is negative and we have a spontaneous reaction, negative, what that means is that this must be negative, meaning the natural log of the K must be positive. So the K must be greater than 1 because the natural log of a number greater than 1 is positive. And so when delta G is negative, that means that K is greater than 1. And that means that you have more products at equilibrium reactants. So for the K to be greater than 1, it means C and D concentrations are greater than A and B multiplied by E. So K is greater than 1, that's a negative. Delta G is positive, so a non-spontaneous. That means that the natural log of Q must be less than, or so it must be Q is less than 1 because the natural log of a number less than 1 is negative, and negative times negative is positive. And so all of these things, what I've shown you here, all of these things I've shown you, this right here, and this analysis, these are not things you should memorize, right? You should not memorize this chart per se. You should be able to reproduce it for yourself by analyzing this equation. And same here, you should not memorize what I just put here. You should be able to understand it yourself based on the math, right? If this is natural log of a number greater than 1 is positive, so that's a negative total side, so negative delta G. Natural log of K less than 1, that's negative, so negative times negative, positive. And we can see here, when delta G is very, very negative, your K is large and greater than 1, right? So the first example I gave was here. If delta G is 0, K is 1, so we have 50-50 products and reactants. Same C, D versus AB. Delta G is very negative. That means a large K greater than 1. It means very spontaneous, so lots more products at equilibrium than reactants. Whereas if delta G is very positive, that means that K is much less than 1, meaning there's a lot of reactants at equilibrium. Not a lot. So that's going to conclude the first lecture here. This first lecture was about delta G and spontaneity and how we can predict if a reaction is spontaneous or not. Next, we're going to talk about how we can know if a reaction is fast or not, whether it's fast or slow. That has to do with chemical kinetics, and we'll start that next time.